we're in a situation where we're talking about Doppler effect. And of course, there are interactives, there are simulators, and you can find them on our online platform where we can have an object zooming towards a listener or an object zooming away from a listener. And what you'll see in all these simulations is this wavelength, this lambda, represented as the distance between concentric ripples, gets spread out as it relates to the listener and noise-making object, the waves that the person is hearing produced by this noise-making object as the noise-making object goes away from that listener. As the object goes towards the listener, the wavelength, the lambda, is smaller. And so we get this idea of large wavelengths being perceived by the listener from whom the object's going away from, wavelengths that are smaller being perceived by the person for whom the object is going towards. And really that has to do with the fact that the noise maker is constantly changing its position. So where my pencil is right now, the largest ripple of sound was made when the object is where the pencil is right now. The second largest ripple of sound, see, this is the center of that ripple. The third largest ripple of sound, it was made here. And the most recent ripple of sound in this diagram, remember this diagram is an animation, was made when the object was here. And so as this object moves along, the wave fronts get spread out behind and bunched together in the front because of the way that animation works. And I really do suggest that you look at the simulation for this as linked online to make sure that you get a visual for what's happening as the video plays, as this animation happens. So the speed of sound is the same for both observers, but the wave separation, the wave fronts are spaced out. And as a result, this observer observes a low frequency. The F observed is low. For this observer, the observed frequency is high. And we make the sound effect of where as it travels towards you, it's a high-pitched wee, and as it passes by you and goes away from you, woo. And if you've ever heard a car zoom past you on a busy street, then we get that idea. Now, if we're going to talk about how we could sort of like act this out, obviously we have cars and trains coming towards us and away from us. In the past, I used to have like a Nerf sponge football, and I had a buzzer inside. And when I threw it at a student, they'd hear, ee. And when they threw it at me, they would hear, ooh. Now, that was such a cool little toy that somebody stole it. Another cool little toy that I had was there was a noisemaker that I would put on the end of a string. Now, you can do this with a cell phone if you care to take like some nylon stockings, and download a tone generator on your phone. And the tone generator will make a constant kind of sound. But if you swing the nylons around your head, maybe you want to do this with something other than your fancy iPhone, when it swings towards somebody who's listening right here, they'll hear ee. But then if you have another person over here listening and it goes away from them, they'll hear ooh. So towards ee, away ooh. And again, just another example of the same original frequency, the actual noisemaker itself, being perceived differently by somebody having the sound maker go towards them as opposed to away from them as you swing that whining cell phone above your head. And this kind of looks like something from a cowboy or something like that, very a lasso over your head. But you'll hear it, ee-oo, ee-oo, ee-oo. It makes me think of almost like a siren. And so we have this idea, and you can zoom in your own notes, look a little closer. Here we have maybe a better illustration of what I was talking about earlier with these two listeners, where these concentric ripples, these wave fronts, were created at moment 1, 2, 3, 4, and so on for each of these concentric numbered circles. Concentric number 1, 2, 3, 4. A person located at position A is going to hear a low frequency, large wave fronts, and a large separation between wave fronts, large lambda. And B is going to hear a high frequency, a small separation between wave fronts. And so these wave fronts are going to smack into B, something like boom, 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 boom. Whereas the wave fronts that are going to smack into A are going to be more like boom, 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 lower frequency. Remember, the word frequency and frequently come from the same root word, frequent. How frequent do you encounter these compressions? Now, as we move on down in this conversation, we got to talk about I got a little bit of information coming up before I need it, because obviously this is me just talking through a note that had already been written through. Sadly, the original recording didn't work out, so I'm just doing a quick recap here. The idea is that when you move away from a fixed source of sound, the frequency of the sound that you hear ends up being less than what the sound emits. If you go towards, it's going to be higher. And so this is an example of maybe a nice little multiple choice question. You should be able to think through a multiple choice question like this one and deduce what the correct answer is. Now, if you're listening to the Doppler effect, I'm going to cover this up, and I just want to talk about what's happening in the in-between. We have an equation for what the observed frequency is relative to the original frequency. And what we have in between here, this, we'll call it a modifier coefficient for the Doppler effect. Within these brackets, we have the modifier that allows us, just as a multiplier, to modify the original frequency so that we can talk about what the observed frequency is. That's the frequency heard by the listener. We have the speed of sound plus the speed of the listener, the detector, divided by the speed of sound plus or minus the speed of the source, the origin of the sound, if you like. Now, for us, in this course, we're going to let the detector have a speed of 0. In other words, all of our listeners are going to stay still. It just makes the math a little bit easier for us, but I couldn't not present the full equation. And so when we talk about our frequency observed by a hearer, we'll talk about the speed of sound plus or minus the speed of the source. Now, when I look at this, I've got this denominator where we have to choose plus or minus. I'm going to tell you, we're going to use the plus sign when the object moves away. I want to talk about the rationale for how we know that. Let's think about it. When an object moves away, the perceived sound is going to be low. It's going to be a smaller observed frequency than the original. Well, how are we going to deal with that? Well, let's think about this. I would use the plus sign in the denominator in that situation, and my rationale goes like this. For example, if I was adding in math class a 3 plus 2, plus sign, notice, it results in a fraction of 1/5. Now, 1/5 is a small number. If I, comparing, if I use the minus sign instead, 1 divided by 3 minus 2 is just 1 divided by 1, or 1, a comparatively larger number. So here we're talking about a decimal value of 0.2. Here we're talking about a decimal value of 1. Clearly, if I use the addition in the denominator, the fraction ends up being a smaller value. If I do the subtraction in the denominator, the fraction ends up being a larger value. And again, let's go back up to this picture. That means that when we're going away from somebody, they end up hearing a lower, smaller value, a lower frequency. When the object goes towards the listener, they hear a higher, larger value, frequency. And so we're going to use the plus sign in this equation when objects are going away from us. We'll use the minus sign in this plus or minus when objects are traveling towards us. And so that's just like a quick rationale on how we would decide whether to use plus or minus in this equation. Now, what would happen if an airplane was flying straight at us and sped up? Well, we think about this speed of sound, speed of source. If the object speeds up, then we're going to end up having a increased frequency if they're traveling towards us. Notice in our diagram, the lines, the wavefronts would be bunched up more if the source is moving faster. And again, if you want to play with the animations on this one, take a look at the simulation links that are added in our online platform. So we end up having a higher frequency that gets heard. Now, other ways that we could talk about this, question might be phrased as, would the frequency you hear be faster or slower? Now, I don't know too many people that talk about frequencies that way, but I've seen the wording before in the questions. When we say faster, we mean higher frequency. When we say slower, we mean lower frequency. Now, if I was crafting a question myself, I probably wouldn't say faster frequency and slower frequency, but the intention here is higher frequency and lower frequency. What does the plus and minus sign mean? Again, we're just recapping what we said already. We use the plus sign in this equation in the denominator. When an object is going away from us, we use the minus sign to determine the observed frequency by the listener when the object is coming towards us. And again, if you just have a little bit of a language issue with what towards and away means, this is an example of a fire truck going toward a listener. This is a fire truck. Oh, sorry. I'll put that on screen. A fire truck going toward a listener on the left and a fire truck going away from a listener on the right. And what do we hear as it comes towards you? We hear, woo! wee. And as it goes away from us, woo, lower frequency as it goes away from you. And the cartoonist did a pretty good job here of showing the wavefronts being closer together as it approaches and farther apart as it drives away. And so that was a quick run through, and I hope that it's helpful.